Okay, so we're going to wrap up our thing on strengthening. Wednesday, we're going to have a quick quiz on structure and get right into the depths, right into aluminum. And we're going to it'll beautiful, right into the thermodynamics of precipitation and aluminum alloys. So we'll have a little bit of review at the beginning there, because everyone forgets, and it'll be new for the welding students, and maybe new for some of the graduate students who haven't taken the core thermodynamics course yet, if there's any in here. So we'll hit it there. Also, just an announcement. We're going to be having a cool trip in the spring. So there will be a metallurgical field trip that's currently being organized, and it will be a 2-day event. The first day we'll all get on a bus. Well, it'll be capped at 25 people, right, unfortunately. But the people that go will hop on a bus here, go to somewhere in Ohio, maybe Midwest Forge or something like that, spend the day seeing cool stuff, then back onto the bus to go to Chicago, have a cool evening in the city, and then spend the second day at Finkelsteel in their arc melting and open die forging facility. And I was just there and saw them quench 150,000 plus pound ingot that just came off the forge lines, right? So when they have an 800-ton open die forge press, right? So really, really big stuff. So it will be sometime in the spring semester. We have some industry funding. I'm just trying to sort of gauge an interest. So if the cost per student for the 2 days was between $50 and $75, how many people think that they would be interested? Okay, fair enough. So students who've taken this class or the PhysMet lab, like when it comes up, we'll have first dibs at signing up before it gets opened up to the rest of the department. I'll keep you in scope with the dates. This is a trip people from Colorado School of Mines have been doing for quite some time. They fly from Colorado to Ohio and Chicago, right? And they managed to fill up the 25 seats each time. So we want to beat them because it's like our home turf. And the CEO of Finkelsteel is an OSU alum. He won our Distinguished Alumnus Award last year. Mark Shirley. Did anyone go see his lecture? Okay. Well, it was really good. Okay, so, the attendance sheet, yeah. Pass that around. Thank you. So solid solution strengthening, right? Real fast, we're going to go through solid solution strengthening pretty quickly and precipitation strengthening pretty quickly, and then we're going to hit both of these again with aluminum and steel. So we'll review these topics sort of over and over again. The main idea here with solid solution strengthening is we're putting in substitutional, or we're putting in solute atoms that create stress fields that interfere with the dislocations, right? So we can think about this. If we put in a small solute atom here, it causes a lattice distortion, but that lattice distortion is symmetric about this solute atom. So we're going to call it a spherical distortion, right? It's sitting on a lattice plane. And this is a weak obstacle, right? And let's consider we have an edge dislocation here, and there's a slip plane and a small, slightly smaller than a small solute atom sitting there, right? So this interaction here is going to be, the interaction energy here is going to be negative, right? Because we have a state of compression up here, and a small solute atom is going to relieve that compression. The atoms aren't going to be quite as confined when there's a smaller atom in that extra half plane. Does that make sense? Right? Just geometry. Okay? So this dislocation is going to be attracted to this region here. Right? But what if this small solute atom were directly below the slip plane? What if it were one atomic plane down? Now we have atoms in a state of tension because they're too far apart. And if we put a smaller one in there, that's going to make it worse. So that edge dislocation now would be repulsed from that if this solute atom were simply one atomic plane lower. Right? What about if this were larger? It would be repulsive in this state, but attractive if it was one down. All right? Everyone okay with that? No major issues with, right? Just geometry. Okay, so how does this give rise to strengthening? Right? So, because on average, if we just stick with smaller for a second, the atoms are distributed randomly throughout our matrix, right? And we don't know a priori where the dislocation is going to come in. There's just equal probability that it's going to be either above or below the slip plane. So those attractive and repulsive things should balance out, right? So how does that give rise to strengthening? Yeah.
So we're talking about substitutional solid solutions.
Yeah.
And according to the Coherency rules, the size difference has to be within 15%.
Yep.
So the size difference to me does not seem like such a big difference for there to be much of a drive.
15% is big, right? So I mean, think about elastic strains, right? A 15% change in size gives you a bond stretch divided by 2 on equal sides, so that's 7.5%, right? So that's sort of an upper limit of stretch, right? That's pretty significant, right? So small differences in size can still have a pretty big effect, and it is a fairly weak obstacle, right? We're going to put a whole bunch of these things in, right? But we have to remember here that the dislocation line isn't perfectly straight. It can bend, right? And there is a penalty to pay when it bends, the line tension, right? But as long as the radius of curvature of that bend is pretty small, that cost is very low, right? So as long as it's moving over tens to hundreds of Berger's vectors lengths, the line tension penalty is very small. And if you think about a 1% alloy, right, the alloying elements, the alloying atoms are fairly well separated, right, long compared to the Berger's vector. So what happens is the dislocation tends to want to stay near the attractive regions. You'll have to give extra force to move that part of the dislocation away from where it's attracted to. And it will stay away from the repulsive regions, the positive energy regions. And you'll have to give it extra energy to push it past those regions. Right? So you get strengthening effects from both above the slip plane and below the slip plane, and positive, bigger and smaller, simply because the dislocation line can move, can bend, and your dislocation wants to be in those low energy configurations. And you have to give it extra force to move it out of those low energy configurations into the high energy configurations. Right? This is the same thing that happens we'll see happens in GP zones in aluminum, which are clusters of atoms, right? We have a similar type thing. So there's one subtlety that we need to take into account, right? This was for an edge dislocation. So the stress field for a screw dislocation is pure shear. So there's no dilatational component, right? So that means there is no size effect for pure screw dislocations. Only dislocations that have an edge component feel a size effect from substitution of solid solutions. Right. There's some other small things with that you can get from DFT calculations, like electronic interactions and things, but we can ignore those for right now. Okay. So those are for what we call spherical distortions. Some point defects are what we call tetragonal distortions. And the important tetragonal distortion that we'll talk about is a carbon atom in BCC, right? That is interstitial. So interstitial in BCC gives you a stress field that isn't symmetric. And those are very hard distortions. Nitrogen and niobium. Interstitial oxygen and titanium. These are sorts of things that cause that the size effect is a much stronger because of the geometry of the crystal. And we'll talk about those more as they come up in the individual systems, right? So how big of an effect is it? Well, if we can define a strain-like parameter that gives you the difference in lattice parameter per unit concentration of having the substitute in. And you can see that it goes as the radius of the matrix to the cubed, and then times the strain parameter, right? So that's the just sort of gives you a magnitude for it, right? And so if we substitute all this in, we get something. This is our energy for edge dislocation, R cubed, the parameter, the angle between the slip plane and the atom makes over the distance, and then Poisson's ratios in here. This is like your dislocation core width terms, right? And this is the general form. So the big thing, it's going to be GB times this strain term is the important bits. Okay. So we also have, I mentioned on Wednesday, we also have a modulus effect, right? And right, remember the energy of a dislocation is GB squared, right? So if your dislocation gets near an atom where the bond stiffness between the solute and the matrix is different than the matrix, you're going to affect the energy of the dislocation in that region because your bond stiffness is different, right? So we saw size effect is always a negative interaction. If we have a compliant solute, so if we have a stiffer bond, that's also going to be a negative interaction. But if we have a stiffer bond, that gives us a positive energy, right? Because we're always, when we talked about size effects, it depended whether you were coming in under or over, and it was a statistical argument about the dislocation wanting to be away from positive and towards negative, right? But if you have a stiffer atom, it's always positive everywhere, right? So you're going to have a destructive energy, right? In the reading that I put up, the language is confusing, right? So the book says a hard atom for stiff and a soft atom for compliant, which means that a hard atom is a weak obstacle and a soft atom is a hard obstacle. So just beware of the terminology there when you read the chapter. It can be a little confusing. Right, but the magnitude of it is basically going to be a strain-like term, which gives you the change in shear modulus per unit of solute concentration. So this is a dimensionless term that is like strain. And it's going to be proportional to that, and the Berger's vector squared, and the radius, and the distance squared. So it's 1 over r squared term. So it's a much shorter range effect than the size, right? And it's always going to be combined rather than destructive, right? So the idea of what you want is if you have an optimal strengthening solid solution, you would want an atom with as big of a size difference as you can so that you don't get phase separation, right? And you want it to have your solute atom, your alloying element, to have a lower elastic modulus than the alloy that your primary element, right? Which is fine for steel and titanium. You can't quite get that for aluminum, right? Right, which is one reason why precipitation strengthening aluminum has more precipitation strengthening elements or alloys than solid solution strengthening alloys, simply because you can't get a big bang for your buck because you can't take advantage of the modulus effect as well. There's also a lot to do with the solubilities of alloying elements. And so this is just one reason why precipitation strengthening in aluminum is very important, right? And this just shows you examples of the magnitudes that you can get out, and the difference between, say, that carbon and iron gives you a much stronger than direct substitutional because of the nature of that stress field. But we'll talk about that more in those particular examples. So particle strengthening is,
just a question. For both of the attractive and repulsive,
yeah,
they both reduce the dislocation movement. Yeah, but attractive reduce more than repulsive.
No, it's the simple fact that when you're talking about the size effect, you always have a mix of attractive and repulsive, because depending on where it is on the slip plane. So your dislocation will always seek to find a low energy source, right? Whereas with the modulus effect, you're always going to be all positive or all negative, right? And so the lower the energy, it takes more to cut to move away than to be repulsed, right? So in terms for particles, we want particles that are hard to cut and hard to bow around, right? In an ideal world. So if we think about what that means for a given volume fraction, we want particles that are close together so we can't bow around them. And we want particles that are big enough that they're hard to cut through. All right? So what we want is a nice dispersion of fine particles. We'll talk about this a lot with aluminum. We talked about boundary coherency before with interfaces. So in general, a coherent interface is going to be much easier to cut through than an incoherent interface. right? Because we have a nice path we don't have to change our slip plane, right? When going through, right here, our dislocations are going to come in and interact with other other interfacial dislocations, and we might have a misorientation, and we're going to have to change directions, and we have dislocation reactions. So all that makes incoherent interfaces much more difficult to cut than coherent interfaces. Okay? So we have a couple different effects that come about, right? We have coherency, right? And which is basically what I just said. So you have the interface, we have strain, there's an elastic strain field. Coherent interfaces tend to have a higher strain field. We go through this in the reading. The main thing I want you to take away from this is not how these equations look, right? Just knowing what the effects are and being able to say, oh, that's a small particle with a coherent interface. It's not going to be too hard to cut, right? Okay. We also have modulus hardening, right? Which is the same argument that we made before. If I have a particle that has a different shear modulus than my matrix, once the dislocation starts to cut into it, it's going to have a different energy than the dislocation in the matrix, right? So that's going to cause the dislocation to either resist going in or want to stay in and cause you to have a bend, right? And so the modulus hardening is the second sort of primary precipitation strengthening effect that we have to worry about, right? And again, here for reference, and you can go through it in the reading, is sort of some details of the magnitude, right? And again, all these follow the same sort of thing in the reading. There's this dimensionless parameter which takes which is like an elastic, which is like a strain. It's a strain-like dimensionless term. It's not really a strain because it has nothing to do with the displacements of atoms, but in terms of energetic calculations, you would use it in place of strain. But it's always a dimensionless parameter that gives you a difference. So in this case, it's the normalized difference between the shear modulus of the particle and the matrix, right? And it's typically you're going to be proportional to that, to some power. In this case, it's the 3/2 power. Right? And then we have another effect, which is chemical strengthening, right? Which is not a very good name. I would have called this surface energy strengthening or something like that. But chemical strengthening is kind of an old name. Yeah.
For modulus hardening, the interface is not coherent, we will not consider the difference.
If the
Interface is not coherent.
For modulus hardening.
Yes.
So if it's incoherent, it will generally be much smaller than what you have to pay to get through an incoherent interface. So you can generally neglect it then because it will just be smaller. Right, but the fact is,
But by incoherent, you cannot really cut through the.
You really can't, because the dislocation has been changed by passing through the interface. Right, it's not the same dislocation in the particle as it is on the outside. Right, so it's not really the same thing. Right. For this, we just sort of want to go over general effects, so we have a framework to talk about these things, right? So chemical strengthening is another effect, and this is generally pretty small, at least if only one dislocation goes through, right? Or if the particle is very small. Because when the dislocation goes through, we shear our particle and we make a step which is now new interface, right? So there's an energy penalty that has to be paid, right? The surface energy per unit area of interface. So by cutting this, we're making new interface. We have an energy cost associated with this. So if the particle is very large, the amount that we're increasing the surface area is very, very small, right? So it's kind of negligible. But if this is a very small particle, say tens of Berger's vectors across, like say GP zones in aluminum that we're going to be talking about, this can be a pretty big effect. Also, if you have dislocations, if you think about a dislocation source, a Frank Reed source that's pumping out dislocation after dislocation, they're all on the same plane. So generally, you'll have a particle that's cut by multiple dislocations, each one making a step, right? So in that case, you can add a pretty significant amount of surface area, right? Of course, if you do that too many times, then you've destroyed your particle, and, right? Then it becomes softer. But initially, you can create a pretty big increase in surface area, right? And again, it's the same thing. We've got a term, this is the amount of surface new energy, a fractional amount of new surface energy that's going to be created, right? And then we have a really important one, especially this is going to be super important in nickel superalloys, order strengthening, right? So here we have an ABA stacking sequence, and if a dislocation comes through, now we have a stacking fault, right? So we have to pay the energy cost of creating this stacking fault, right? Of course, if a second dislocation comes through, it'll reorder it. But of course, remember that most of the time, we're not talking about full dislocations. We're talking about partials. And in superalloys, it's a full dislocation is a partial in the ordered phase. And then if you break that up into Shockley partials, you can get all kinds of complex faults based on the order that you pass the partials through. So this can be really a big effect because you pass dislocations through and you're not going to get back to your original layout. But if you just think about a full edge dislocation passing through, the first one will create a stacking fault. The second one will bring it back. All right. Okay. And then the last thing is non-deforming particles. The analysis for this, for Boeing, is exactly the same as it was for our Orawan source, except our pinning particles, our points are now particles rather than, say, dislocation jogs, right, or a change in the plane. So the analysis is exactly the same, right? Our effective distance between that we're extruding, that we're bowing through, is the separation of the particles minus 2 radii of the particle, right? We go through, and then after we bow, we now have 2 loops, dislocation loops, left around these particles. So that effectively makes our distance smaller. So the next dislocation will be extruding through a smaller distance here, right? You'll have to deal with the dislocation interactions. And the analysis becomes a little more complicated then, because you have the dislocations will be of the same sign, so you have a repulsion here, but it's, right, the repulsion is the distance is going to depend on the force, and But you can imagine after you pass a bunch of these through, and now you've got these concentric rings of dislocations around these particles, it can get quite difficult to move another dislocation through that really narrow area. Okay? And if we think about this, the general, just sort of, this is the important picture, right? Generally, there's a competition between bowing and cutting, right? If we keep our volume fraction the same, as we make our particles larger, the separation between them gets larger, right? This is Ostwald ripening, right? Which we'll talk about in aluminum as well. Right, as we make our particles bigger and our volume fraction remains constant, our separation between them gets larger. So that means the larger we make our particles, the bigger the space, the easier it is to bow around them. So for small particles that are close, it's easier to cut. Big particles that are far apart, easier to bow. And the relationships look like this, right? And so our maximum is when the bowing strength and the cutting strength are actually equal, right? That's where we get the most amount of strengthening. Because if we got our particles larger, now bowing becomes easier and we actually have a decrease in strength, right? If we make our particles smaller, cutting becomes easier and we have a decrease in strength. So for precipitation strengthening alloys, we tend to call this peak aged, right? When we're right at the balance between where cutting and bowing is exactly equal. And we'll look at a lot of examples of that with aluminum. So we have a couple minutes, finished just a couple minutes early. I'm going to give just a little bit of introduction. Just a little bit of introduction with aluminum, and we'll get out of here a couple minutes early for the Labor Day weekend, and we'll come back Wednesday. But this starts the real, I'd say, the meat and potatoes of the course, right? This is where we really get into it. And aluminum is why am I starting with aluminum? Right? No, I mean, right? There's a couple really good reasons. So pure aluminum is basically single phase FCC over all useful temperatures and pressures, right? Whereas steel or pure iron, even if we ignore the carbon part, goes through temperature-dependent phase transformations, right? So from a teaching point of view, let's add one complication at a time. So let's start with an element that is a single phase, FCC, so it's not even a weird phase, right? It's the easiest, because we only have to think about one slip system. We never have to worry about twinning, right? We don't have to worry about Martin-Siddick transformations. We don't, right? And we can focus on precipitation and solid precipitation effects and solid solution effects. Then once we have that down, we can go to steel, where we add allotropes and other phase transformations into the mix, right? So aluminum is actually really important. It's the second only to steel in tonnage used, right? In terms of volume, it's pretty, right? Because the density is so much lower than steel, right? A huge amount of volume. It's the most abundant element in the Earth's crust. It's really hard to get out, though. It's very energy intensive to go from aluminum oxide to metallic aluminum, and it wants to go back there really, really badly, right? I mean, it came from dirt, it wants to get back to dirt. If you look at the Ellingham diagram and the electrochemistry potentials for aluminum, it's right. However, it does form a really nice protective oxide coating, which for a lot of what we do, for our purposes, that's a very good protection against corrosion. Unfortunately, we'll find most of the alloying elements that give us good precipitation properties also destroy our corrosion properties. So aluminum copper 2000 series alloys, absolutely horrible in corrosion. Right? We're putting in beautiful galvanic couples into our material. Okay, so I say that we are FCC at all temperatures and useful pressures, right? So we don't have a ductile to brittle transition like we do in steels. And if we look at the phase diagram, we can see that at room temperature at about 200 gigapascals, we go to HCP. We go from FCC to HCP. And then at about 400 gigapascals, or a couple million PSI, right? I think 400 GPa is like 63 million PSI or something or like that. So really, really, really high pressures, it goes to BCC, right? Which, when I first learned this, completely threw me for a loop. Why on earth would it go to BCC? It goes from a close packed structure to a non-close packed structure. And I had to do a lot of reading to figure out what was going on there, right? Does anyone have any idea why BCC is such a stable high-pressure phase for a lot of metals? Zirconium does the same thing. It's HCP, you put it under, and titanium, right? Under really high pressures, both of those become BCC as well. Right? It actually has to do with the number of second nearest neighbors, right? So it's close packed. FCC and HCP are close packed with respect to the first nearest neighbors, right? But if you look at the number of neighbors within a given radius that includes the second nearest neighbors, BCC can actually be more densely packed than HCP or FCC. It's kind of an interesting little trick on our geometry, right? Because when we think of a close packed plane, we have one atom completely surrounded by 6 other atoms. And that's like as dense as you can get. But if you extend that diameter out to a second neighbor and you go around and you count the number that you have there, then you do that in BCC, you'll see you actually have more atoms in your circle in BCC than you go in HCP. It blew my mind when I discovered that. Well, I mean, I didn't discover it when I learned that, and then I thought I was like super clever because who else would ever bother to look that up? So I was sitting in a candidacy exam, and I asked that question, and Professor Windle's like, "Oh yeah, it's obvious. It has to be the second nearest neighbors." I wanted to punch it. But right. So the other thing that aluminum has for it is it's really easy to form. We can cast it, we can do sheet forming, and powder metallurgy routes for processing aluminum, right? Aluminum is really interesting to me because since I do computational mechanics, a huge part of my field was actually developed to solve the problem of deep drawing in aluminum, right? So a huge chunk of the work done in crystal plasticity was designed to make beer cans less expensive, right? Because you get, because of the anisotropy of plastic deformation, you got these what are called earring, right? When you deep draw, you start as a circle, you draw it down, and now you've got all these ridges at the top of your can that you have to cut off. So we're looking for new processing routes that when you did that, it gave you a nice flat top instead of a rigid top that you didn't have to remove. So if we just look at some properties here and compare, this is 1018 carbon steel and 2024 and 6061. So 2024, what's this alloy? This is aluminum copper, a very famous alloy developed during World War II for aircraft skin, right? Very high strength at the time. Unfortunately, really, really bad in corrosion. The way they get around that is to plate a layer of pure aluminum on top of the aluminum copper alloy, so that you still get can get some corrosion protection then, right? 6000 series aluminum, 6061. This is what your bike frame is made out of, right? So if we just look at it, we see the big changes in modulus versus steel, right? And the big thing is if we look at the specific moduli values, right, which is normalized by weight, aluminum actually does pretty good compared to our steel, right? Which is one of the reasons why we use aluminum so much, because in terms of specific strength, it's pretty strong. The big issue, right, if we look at the relative cost with respect to steel, depending on the alloy, 9 to 15 times the cost of steel, right? But not nearly as bad as titanium, right? 66 times, right? So the big, right? That's the big driving force for more and more aluminum use is this high specific strength and low density, right? And then I think we will actually stop there for today. We'll get into this. It's interesting, the number of alloying elements that you can use in aluminum is very restricted compared to some other systems, simply because the solubilities are so low. You tend to form lots of intermetallics. So we'll start to discuss that and then jump into our big thermodynamics review on Wednesday. So enjoy the holiday and try not to think about this stuff too much.